Hello everyone, this is our lesson on section 2.6, graphs of rational functions. So our learning targets today are, first of all, we want to identify what a rational function is. We want to use transformations of the reciprocal function for graphing basic rational functions. And then we're going to look at how to find asymptotes and graphing more complex rational functions. So first of all, what is a rational function? A rational function is just a function with, you see the word rational, written in form of a ratio or a fraction. So we have a polynomial in the numerator and a polynomial in the denominator. So first of all, I want to look at the simplest rational function, 1 over x. So if we look at 1 over x, think of just the points you would graph and the points you can't graph. So if I have 1 over x, what can my x not be? My domain. My domain is x cannot be 0. And I'm going to have an asymptote there. So let's draw the asymptote. I'll get out a ruler. And now let's look at some points. When x is 1, y is 1. When x is 2, y is 1/2. When x is 3, y is 1/3. And notice it's going to get closer and closer and closer to the y-axis, but it's never going to be able to reach. And then if we look at the reciprocal, if I plug in 1/2, well, 1 over 1/2 gives us 2. So 1/2 is 2, 1/3 is 3, and so on in that pattern. Let me make it a different color than the asymptote. And my graph looks something like this. Now, my x equals 0 is an asymptote, but also there is never a value that I can plug in to get what? To get y equals 0. So I'm going to have another asymptote at y equals 0. Now, if I go ahead and I plug in negative values for x, wrong color, then I'm going to get all the negative values for y. And I'm going to have the same thing in quadrant 3. So my domain again was x equals 0. My range is y cannot be 0 because there's no value I can divide 1 by to get 0. My asymptotes are at x equals 0, y equals 0. My function is always decreasing as we're going from left to right. There are no extrema because they go to infinity in both the positive y direction and the negative y direction. And they get ever increasingly closer to y equals 0, but they never reach it. And it is symmetrical with respect to the origin. And that's your basic parent function, y equals 1 over x. You should be very familiar with that. And we had that at the beginning of the year. I think most of you are familiar with that. Now, we can have all the translations of the other functions. So we can have the vertical shift, we can have the horizontal shift, we can have the stretch, and we'll go through each one. And how do we do that with a rational function? Well, keep in mind, are asymptotes. And when you want to graph a function like this, a reciprocal function, do the translations on your asymptotes first. So what if we want to shift to the right 3 units? In this case, we are going to replace x with x minus 3. And what I do there is I take my normal asymptotes and I'm going to shift to the right 3 units. Sorry, this ruler is okay to manipulate. Not fabulous. I lost my 3. Let me make this a little bigger. There we go. So my asymptote has shifted right 3 units. I still have my horizontal asymptote y equals 0. If you move that 3 units, it doesn't really affect it. And now I want to graph my points. Think of them as in the same relation as what we did before. If I plug in, you can do your table if you'd like. But if I plug in 4, 1 unit to the right of where my asymptotes cross, well, if we look up here, it was over 1, up 1 to get to this point, 1, 1. The same idea, over 1, up 1, left 1, down 1. But you can plug in the points. 4 would give you 1 over 1, which is 1. 3 would give you, 2 would give you 1 over 2 minus 3, which would give you negative 1. And you'll have the same pattern. We have just taken our graph and we've moved it to the right 3 units. Do that by first moving your asymptotes. How about a shift up 6 units from the original graph? So I am going to take my original parent function, and when we shift up 6 units, we add 6 independent of the x. So in this case, I want to shift my asymptotes first. And now, since we don't have a shrink or stretch, the same proportions hold. From where the asymptotes cross, up 1, right 1, left 1, down 1. And then we draw my graph. Should make it a little bigger, in the same proportions. And if you want to plug in points, you totally can. When x is 1, y is 7, that's where we are. When x is negative 1, y is 5, that's where we are. And then you could add points as needed. If you had 2, 1/2 plus 6 is 6.5. If you have negative 2, so that's 6 minus 1/2. So that is 5.5. And you see those points reflected in here. How about a reflection over the x-axis? So I have f of x, 1 over x is my parent function. So when I reflect over the x-axis, I want to make all my y's negative. So I want negative f of x, which gives me negative 1 over x. Now, this function is unique in that if we replace x with negative x, which is a flip over the y-axis, we actually get the same thing. And so what does that look like? Well, I won't draw the asymptotes again. They stay in the same place, but it's simply a reflection over the x-axis. It's a little bit sloppy. Oops, sorry. And all the same points hold that we had before, except we have made my y values negative. So I have 1, -1, -1, 1. If I plugged in 2, I would have a negative 1/2. If I plugged in -2, I would have positive 1/2. If I plugged in positive 1/2, I would have -2. And if I plugged in negative 1/2, I would have positive 2. And we get ever increasingly closer to the x and y axis. Stretches, we can do stretches and shrinks. If we want to stretch by a factor of 2, it's simply 2 over x. I haven't moved my asymptotes, so let's look at an x and y table. Remember, y in this case is 2 over x. So when x is 1, my y is not 1 anymore. My y is 2. When x is -1, y is -2. When x is 2, y is 1. And when x is -2, y is -1. So when you do a stretch, think of it, it kind of pulls it away a bit from that 0, which makes sense because when you stretch things, think of it as like you're pulling it from the top. You would be pulling it away from 0 a bit. In this direction, when you stretch, you're pulling it away from the x-axis. So you're pulling that original point away from origin by a factor of 2, and you're multiplying all the y-coordinates by a factor of 2. So how would we write the equation of a rational function, the parent function, with the stretch of 3, and then a shift left 4 units and down 1 unit? So we have our original parent function. We want to stretch 3 units. We want to shift left 4 units and down 1 unit. And when you want to graph something like this, remember to graph your asymptotes first. So my asymptotes are going left 4 units. And my asymptote went down 1 unit. And it's a stretch of 3. So usually when you have a stretch, it's helpful to plug in a few points. Once you move your asymptote, it kind of tells you what points to put in. That would be easy. Notice my asymptote now is going to be at -4, -1. So I'd want to try -5 on either side of the asymptote. -5 is going to give me 3 over -5 plus 4 minus 1, which is -3 minus 1, or -4. 1, 2, 3, 4. Which makes sense if you think about it, because here would be the point without the stretch, and I've stretched up 3 units. So let me erase that part. And then if I would graph on the other side, -3, I have 3 over negative 3 plus 4, which is 3 minus 1, which is 2. Let me get the ruler out of the way. So I have negative 3 and up 2. And let's try another point. How about negative 7? Oops. Negative 7. 3 over negative 7 plus 4 minus 1. Why did I pick negative 7? Because negative 7 plus 4 gives me negative 3. So I have 3 over negative 3 minus 1, which gives me negative 2. And let's pick another one. If I do negative 1, why did I pick negative 1? I picked numbers that work out easily. So I picked negative 1 because negative 1 plus 4 is 3. 1 minus 1 is 0. So at negative 1, I have 0. And then here's my graph. All right, that's our parent function. Now, what happens when things get a little more complex? Well, rational functions could get really complex, and we could spend a whole month on them, but we're just going to go over the basics. So we want to first look at linear over linear. When we have a rational function where the top function is linear and the bottom function is a line, what does that look like? Well, first of all, we always want to determine what happened to my asymptotes. So first of all, we're going to have a vertical asymptote at an x value where the denominator equals 0. So I look at my denominator, x minus 2. I set it equal to 0 and I solve it. I'm going to have a vertical asymptote at x equals 2. So here's my vertical asymptote. Now, my horizontal asymptote. When you have linear over linear, a horizontal asymptote, the quick way to do it is at the y value that's equal to the ratio of the leading coefficients of the numerator and denominator. So right here, 3 over 1. Now, what's really going on here? Well, if I take 3x minus 7 and I divide it by x minus 2, 3x minus 6, negative 1. Notice I have as my quotient, I have the function 3 minus 1 over x minus 2 equals y. Well, that's my parent function. That's my parent function with, right here, a shift up 3 units. But you don't have to go through all that dividing. You only have to know the coefficient of the leading terms. So here I go. Thanks. We're going to use this idea of dividing to find asymptotes with other rational functions. But that's typically what we're doing here. We're just dividing. Again, you don't have to go through all the work of the dividing. You can just look at the leading coefficients. That's where your horizontal asymptote is. Now, Another good thing to find, just because it's simple and easy, is your y-intercept. Plug in 0, I get -7 over -2, or 7/2. So when I get 0, 7/2, whoops, about 3.5. There we go. The x-intercept where the numerator equals 0. So if I plug in 0 for x in the numerator, then I am going to get let me rewrite that. If I set my numerator equal to 0, that is where I have my x-intercept. So think about what we're doing. Where f of x, where my y value equals 0, is where my rational function equals 0. Well, we don't care about what's in the denominator. If the numerator equals 0, that's where my y value is 0. So I have to find that value. That's at 7/3. So at x, it's 7/3, which is about 2.5. Come over 1 here. 2 1/3. And that's my x-intercept. And then that kind of gives you a clue on what sort of quadrants your graph is in. And after that, you can just plot a few more points. So I could put in 1 if you want to get a nice shape. And that would give me 3 minus 7 over 1 minus 2. So if I plug in 1, that would give me 4. Now I have a couple of points. And these are asymptotes, so I know the ends are going to get closer and closer to the asymptotes. And you can plot as many points as you want to get that rounded shape. Usually if you do maybe 2 a section, that should be good to get the shape. So maybe we want to plug in 4 to get this actual point where this point exists. So if I plug in 4, 3 times 4 is 12, minus 7 is 5, 4 minus 2 is 2. So at 4, it's going to be about 2.5. So it's going to be a little bit closer. So I was a little bit further away just by eyeballing it. So it'd be something like this. All right, that's what happens when we have a linear over a linear. So again, to recap, you're going to have a vertical asymptote wherever the denominator is 0. You are going to have a horizontal asymptote, and you can find it quick and easy. You don't have to divide, just look at the ratios of your leading terms, your leading coefficients. You're going to set x equal to 0 to find the y-intercept. You're going to set the numerator equal to 0 to find the x-intercept. And then you're going to find a couple extra points just to give a good shape to your rational function. Okay, next up. What if we want a rational function where the degrees are the same, but they're not necessarily linear? So let's give an example here. In fact, let's change colors so I don't run into what's up above. So if I'm going to do f of x equals 4x squared plus 2x plus 1 all over 8x squared minus 6. Good grief, what in the world would this look like? Well, first of all, vertical asymptote, again, is the x value where the denominator equals 0. So I take 8x squared minus 6 equals 0. So my x is going to be plus or minus the square root of 6/8, which is 3/4, which is plus or minus the square root of 3 over 2. And then, of course, for graphing purposes, I'm plugging it into my calculator right now. Square root of 3 is about 1.7. Divided by 2, you get about 0.887. So plus or minus 0.87. So that's where my vertical asymptotes are. How about the horizontal asymptote? Well, the horizontal asymptote is again at the y value that is equal to the ratio of the leading coefficients. If you want to divide it out, you can. It's too much work. Just look at the ratio of the leading coefficients, 4/8 or 1/2. My y-intercept, just plug in 0 for x. So f of 0 is going to be 1 over -6. And my x-intercept is where the numerator equals 0. So I have to look where my numerator equals 0. And I am going to look where 4x squared plus 2x plus 1 equals 0. And at that point, you could just use the quadratic formula, or you can go ahead and factor. So in this case, negative b, negative b is -2, plus or minus the square root of b squared minus 4 times a times c over 2 times a. As you can see, we're going to have a negative under the radical, so it's not going to intercept. So there's none. No x intercept. Now, let's see what happens here. I think for our purposes, hopefully this doesn't throw anybody off. Since the graph is so tiny and my vertical asymptotes are at 0.87, which is rather tiny, I'm just going to, let's make our 1 right here. So how many units did I go for? 1, 2, 3, let's make it a little bigger. And we'll make my 1 right here. So ignore the numbers on the graph. We're going to use these numbers. 1, 2, 3. And we'll make 1 up here. Sorry, this will be -1. And we'll make this -1. It just makes our graph a little bit larger for us. All right. So get our rulers out. 0.87 plus and minus are where we have our vertical asymptotes. So just estimate where you think 0.87 would be. And positive 0.87. And usually we label them. So I have x equals -0.87, x equals positive 0.87. Now we have our horizontal asymptote. That's at y equals 1/2. So I come up here, I find about 1/2. Let me move that out of the way. And so notice now we have divided our coordinate axes into 6 sections. So at this point, you are going to be looking at plugging in some points to find where it appears. Because I don't really know which of the 6 sections it's going to appear at right at this moment until I plug in some points. So I'm going to calculate my y value given certain values of x, and you're probably wondering, well, what values of x do I pick? Well, pick some values of x that make sense. That makes sense according to your graph. So I erased my equation. Let me write it back over here where it's not in the way. 4x squared plus 2x plus 1, 8x squared minus 6. So we already found out our y-intercept when x is 0 is at -1, 6. So I'm going to do the -1, 6. It's really close to the x-axis. And now I already know it's in this quadrant, this middle lower quadrant. And at this point, since I have asymptotes on either side and I know it's in the lower quadrant, I'm pretty sure it's going to be going this way. Sometimes they can cross asymptotes, but then you could pick a value on either side. So you could plug in 0.5, you could plug in -0.5. So on my calculator, it takes a little bit. So I have 4 times 0.5 squared. 2 times 0.5 is 1, plus 1 is 2, and it gives me 3. And then on the bottom, 0.5 squared times 8 minus 6 gives me -4. So I have -0.75. So at a 0.5, this is about -3/4. So probably a little off there. So it comes down toward the asymptote this way. If I plug in the -0.5, I have 4 times 0.5 squared. -0.5 would be -1 plus 1. So this gives me 1. And then in the denominator, again, I would have -4. So -0.5, -1/4. But then it's going to turn and go toward the asymptote. Now, experience tells me, because I've graphed a lot of these, that usually when you're in the lower part in the middle, you're in the upper right and left-hand corners of the other two sides. But let's check it out. Let's see. Let's take a point like 7 and see where we end up. So 7, I've got 4 times 49 plus 14 plus 1, which is 211. And in the denominator, 8 times 49 minus 6, which is 386. 211 divided by 386 gives us about 0.55. So 7 is about right there. And if I want to do one on the other side, so let's pick something like, let's pick -1 on the other side. I know -1 is outside of -0.87. So if I get -1, I might not get so close to that asymptote. So 4 minus 2 is 2, plus 1 is 3. And in the denominator, 8 minus 6 is 2. So 3/2. So -1, 3/2. That's a little bit higher up. So that gives me a little bit better picture. If I want to do 1, which is outside this positive 0.87, 4 plus 2 plus 1 is 7. And in the denominator, 8 minus 6 is 2. So at 1, it's 3.5, which would be even higher than that. So it would be way up here. And then you fill in with your graph. So it's going to follow the asymptotes. And it's going to look something like this. Now, what would I expect when you're graphing? Definitely, I would expect for you to graph your asymptotes. I would expect that you could plug in maybe 2 points. I would not X for more than 2 because that's 6 points already to give a basic shape. And if one of those points are the intercepts, that's great. Notice we found out because we had a negative under the radical that we didn't have any x-intercepts, which we don't in this case. If we had found right here 2 values, then maybe this graph would have popped up a little bit over the x-axis and given us a couple of intercepts. In this case, the graph does not. And that's how to graph a rational equation, where the degrees on top are equal to the degrees on bottom. Now let's look at a couple other cases. What happens when you have a rational equation and the degree on top is bigger than the degree on the bottom? So what happens in this case? So first of all, let's think of the vertical asymptote. Again, same concept. It's at the x value where the denominator equals 0. So x squared minus 9 equaling 0. It's going to be at x is plus or minus 3. So draw your asymptotes. We'll go back to the normal scale. We tend to draw them with dotted lines. All right, so there's my asymptotes, or plus or minus 3. But now, in this case, where is our other asymptote? And we don't have a horizontal asymptote. When the degrees aren't the same at top and bottom, there is no horizontal asymptote. There's what we call an oblique asymptote, a side-to-side asymptote. And we find it by division. So x to the third divided by x squared minus 9. I have x to the third minus 9x. Don't worry about the remainder. Just look here at the quotient. And that is my oblique asymptote. Y equals x. So I'm going to graph the line y equals x. Now, again, my graph is cut into 6 sections. We have the sections on the bottom, or kind of to the right. This one, this one, this one, this one, this one, this one. We have all those 6 sections. We have to figure out how the graph fits in. And I have to tell you, again, we could spend a month on this, because depending on your rational function, you can get some pretty crazy looking things. So we're just looking at basic principles of how to graph these. So first of all, the y-intercept. Well, the y-intercept is where we plug in 0. So if we plug in 0 here, we have 0 on the top, negative 9 on the bottom, which is just 0. So this one crosses right here. Let me change my color to graph. which is kind of odd. It's crossing my asymptote, but sometimes that happens. The x-intercept, where the numerator equals 0. Well, where x to the third equals 0 is where x equals 0. So my x-intercept and y-intercept are right at the origin. Okay, now I've got to test some other points. So let's test 1. 1 is always very easy to test. So if I plug in 1, I have 1 on top. I have 1 minus 9 on the bottom. If I do 1, I have negative 1/8. All right, that's going to prompt me to do 2. 2 is 8 on top. 4 minus 9 is 5, 8/5, which is a little over 1. So it goes like here, and there's my asymptote. It's going to go this way. What happens if I do the negatives? Negative 1 gives me negative 1 on top, and it gives me negative 8 down below, which is positive 1/8. And if I plug in negative 2, that gives me negative 8 on top. I still get negative 5 below, which is 8/5, which is 1 3/5. And this is what the middle part looks like. Now again, they don't always look like that. Sometimes they might hit the origin and come back down the other side. Totally depends on your functions. So we're just going through some basic skills to see where they lie. Now, let's look at numbers bigger than my asymptote, so bigger than 3. What would happen if we plug in 4? So if we plug in 4, pull out your calculator. 4 to the third is 64. 4 squared is 16. 16 minus 9 is 7. So 64/7, you're talking around 9. So with 4, I know it's going to be up here. And then you might want to pick one other value. So maybe you could pick something like 6. So 6 to the third, that's not something I've memorized. 216. And 36 minus 9 is 27. 216 divided by 27 is 8. So 6 and 8. And your curve is then going to go toward your asymptotes. If you look at the negative part, well, let's plug in a negative 4. If we plug in a negative 4, we would get negative 64/7. What was 64/7? Or approximately 9. So right down here, and if we plug in negative 6, we would get negative 8. And remember, your graph always goes towards its asymptotes. And so there's a nice approximation of this graph. And feel free to put it into Desmos and compare. All right, one other example. What happens when the degree above is smaller than the degree below? So first we did same degrees. Second, we did when the degree in the numerator is bigger than the denominator. Now we're doing when the degree in the denominator is bigger than the numerator. How do we graph this? Well, in this case, first of all, we want to check out the vertical asymptotes again. Any x value where the denominator equals 0. So x squared plus 2x minus 3, where does that equal 0? Feel free to use the quadratic formula. In this case, this one factors. Hopefully you can recognize that pretty easily. It wasn't a very complex one. 3 breaks up into 3 times 1. We have for our middle term 3x minus 1x. So in this case, x can't be negative 3 nor 1. So we want to draw our asymptotes. And here they are. Sorry, this is hard to get straight. All right, a horizontal asymptote. Where's our horizontal asymptote? The horizontal asymptote is going to be at y equals 0. Why is that the case? Well, let's look about this. If we think of the limit as my x is going, let's just think about positive infinity. Notice at the top, we have x plus 2, and down below, we have an x squared plus 2x minus 3. As x gets really, really large, let's say 1,000,000 or 1,000,000,000, this square is going to make the denominator just explode in proportion to the numerator. And so as my denominator gets much larger and the denominator is smaller, this is going to go towards 0. And we're talking for very, very, very large numbers. So we have a horizontal asymptote at y equals 0. So we'll just draw it in right here. And remember, when you're graphing these, it's always nice to label your asymptotes. Y equals 0 here, x equals 1, x equals -3, unless they're clearly marked on your axes. You want to find the y-intercept if 1 exists, so we're going to plug in zeros. F of 0 is 2 on top, -3 below. So when x is 0, we've got -2/3 right there. The x-intercept where the numerator equals 0. So x plus 2, where is that 0? Where x is -2. So right here. And now it's a matter of looking at some points. So again, x and y, pull out your calculators, and let's start in the middle. We already have this point here. We have this point here. Kind of makes me wonder what's going on. So I'm going to try maybe -2.5. I'm thinking it's going to cross something like this. But I'm going to try that -2.5 just to see what happens. So -2.5 plus 2, -0.5 on top. -2.5 squared. Gives me 6.25 plus 2 times -2.5 minus 3 gives me -1.75. Let me check that again. (2.5) squared, 6.25 minus 2 times 2.5 minus 3. Yep, -1.75. Now I have a negative on top and bottom, 0.5 divided by 1.75. And I get about 0.3. It's 0.2857, but on our small graph, 0.3. So, yep, my graph does go over the x-axis at that point. So I've got 1 point above the x-axis, 1 point below. I've got the intersection. I draw my graph from there. Next up, I have the other 4 coordinates to test. So let's test an easy point. To the right of x equals 1 is 2. 2 plus 2 on top is 4. On the bottom, I have 4 plus 4 minus 3. So 8 minus 3 is 5. I have 4/5. You might want to, at that point, try another one. You could do 1.5 to get a value up above. You could do 5. 5 is going to give you a value really close to the x-axis. Let's just see what happens with 1.5. 1.5 plus 2 is 3.5. 1.5 squared is 2.25. Plus 2 times 1.5 minus 3, 2.25 altogether. So 3.5 divided by 2.25, it's going to give me about 1.6. So something about right here. So here is my graph. And then I'll try on the left side. So my asymptote is at -3. So I'd probably try -4. -4 plus 2 in the numerator is going to be -2. In the denominator, -4 squared is 16. Minus 8 minus 3 gives me 5. So -2/5 at -4. And you could try another point if you wanted to round it out. So you have your 2 points. But they're going to hug the asymptotes. And it's going to look something like this. And then when you're doing your homework, feel free after you're done, plug it into Desmos and see if you have